Hi. So today I want to talk about Buckyballs and one of their applications, which is as organic semiconductors and specifically for use in some photovoltaics, and we'll talk about all that. But first, let's discuss Buckyballs in particular. So you've already watched a lot of short, interesting videos on Buckyballs, but to review a few of the properties and maybe introduce some new ones. The van der Waals diameter of a buckyball, which is carbon-60, is about 1.01 nanometers, so really close to a nanometer. You can make a solution of buckyballs by dissolving them in solvents such as benzene, toluene, carbon disulfide, things like that. It's insoluble in water. And when you make a solution of buckyballs, they have a deep purple color, like is shown here, and then when they evaporate, they leave this brown residue behind. In a solid form, buckyballs are bound by weak van der Waals forces into an FCC structure, and they look kind of like this picture over here. That would be super expensive, by the way. And this is the FCC structure that they form, as you can see here. Buckyballs form a brownish solid with an optical absorption threshold of about 1.6 electron volts. They're N-type organic semiconductors, and although they're stable molecules, they can form chemical bonds. And the reason for this is because if, for example, you have an aromatic compound in a plane, then that's where it's most stable. But when it's rolled up into a ball, like a buckyball, any deviation from that planar geometry is going to cause some bond strain, and that's going to result in a higher energy state and hence an enhanced chemical reactivity. So it is reactive, and you can get it to form bonds with other groups like is shown here in PCBM, which is phenyl C61 butyric acid methyl ester. And this is a compound that's often used as an organic semiconductor. I've done some research with some of these compounds myself. Now, it's not the only kind of organic semiconductor out there. Here's some compounds that are also organic semiconductors, and here's a link, and I also posted a link below on your course website that I'd like you to watch talking about the Nobel Prize and some details about the Nobel Prize for Chemistry in the year 2000, maybe some more information than I have time to give here on conductive polymers. So in 1977, electrical conductivity was actually shown in doped polyacetylene, and so that was the discovery there. And then finally the Nobel Prize in Chemistry in 2000 went to these gentlemen pictured here for their work with the discovery and development of conductive polymers. Now, conductive polymers are conjugated polymers. They have double bonds, a lot of alternating double and single bonds in them. And like I said, there's a video link where you can find out more information on why these things are conductive. In 1986, the first organic photovoltaic or OPV cell was developed. And also in that year, the first organic field effect transistor was developed. In 1987, they developed the first organic light emitting diode. So the idea of organic materials as photovoltaics isn't a new one. However, the efficiencies are now climbing high enough for organic photovoltaics that making solar cells out of organic materials is actually feasible, something that people might want to do. So just to do a little bit of review and maybe some further discussion on photovoltaics so that you can understand what we're getting ready to talk about with the Buckyball OPV materials. Here we go. This is a review for your photovoltaic cell. A solar cell basically takes energy from sunlight and then converts it into electrical energy. It's similar to a light-emitting diode, an LED, but it operates in reverse. Basically what you have is you have a semiconductor p-n junction, and a p-n junction diode can absorb a photon of solar radiation by having an electron transition from the valence band to the conduction band. And in so doing, it creates an electron-hole pair. And then if you hook a circuit up to that p-n junction, the holes in the electrons, which are positively and negatively charged respectively, are going to move in order to create an electric current. Of course, they move in opposite directions so that they don't recombine. and the positive current is going to flow from the P side to the N side. A typical silicon type solar cell looks sort of like this. You have an anti-reflective coating, a transparent adhesive, and some cover glass on there. The sunlight comes through. It goes through these coatings because those are all transparent. And then underneath that is sort of a sandwich of an N-type semiconductor and a P-type semiconductor, usually doped silicon, silicon that's doped to be N-type and silicon that's doped to be P-type. And then they have a back contact on there. So this p-n junction sandwiches here. Now it's important to realize that the electron hole pairs can be created anywhere within the sandwich, and then they move to the p-n junction. Okay, and then from there they're pulled off and they can be used as a current to power your, I don't know, hot water heater, or if it's a small one, maybe charge your cell phone or something. Okay, so what happens in a solar cell? Basically, step number one, the photon is absorbed and creates an electron hole pair, right? Like I said, this can be done wherever throughout the p-n junction sandwich. So it shows here a little cartoon where the solar radiation is coming in and creating electron hole pairs in various places, okay? Then it moves and moves into the external circuit. It's going to be pulled to the cathode or the anode, depending on whether it's an electron or a hole. And the hole moves to the junction, pulled in by the internal electric field in the solar cell established by the p-n junction. So if it's on the opposite side, for example, then it gets pulled towards the junction and then pulled into the other side of the sandwich and then moved to the back contact. So that's what happens. And then, of course, if it's here, then the other opposite's going to occur. It's going to get pulled in. The negative charge is going to get pulled in and move through there. All right, so that's what happens. And then at the end, of course, they would recombine. Now, what can go wrong? Well, a lot. First of all, the electron hole pair can recombine before it completes the circuit and produce no useful current. So it gets created somewhere within the sandwich, but then it promptly recombines. The electron and hole recombine with either each other or another neighboring electron hole pair that was created by a different photon maybe, and that doesn't produce any useful current. Okay? So what you need to have in order to have a good solar cell are to have a good lifetime and a good diffusion length for your electron hole pair. So what are those quantities? Well, the lifetime is the average time that a charge carrier can spend in that excited state. Remember, because in order to create the electron hole pair, it has to get promoted out of the valence band and into the conduction band, which puts it in that excited state. So it has to spend a long time in that excited state after the electron hole pair is generated before it recombines in order for it to move through. It also has to have a decent diffusion length, and the diffusion length is the average distance that the charge carrier can move from the generation point before it recombines. So it has to go a decent distance, otherwise it won't make it through the device. So in silicon, for example, which is a very good photovoltaic material, the lifetime can be as high as 1 millisecond, which is actually a long time, and the diffusion length is typically 100 to 300 micrometers, so that's a good distance. So you can make your solar cell thick enough, for example, maybe equal to 1 diffusion length, and then most of your electron hole pairs are going to make it out, okay? So we all know that silicon is sort of dominating solar cells right now, but there would be a lot of advantages to having organic solar cells. First of all, you could make them out of renewable source materials. It actually is a lot of work to create single crystal silicon, for example. They could be recyclable. That's another nice thing. They're flexible, so that would mean that you can incorporate them into clothing or all kinds of applications. People have gotten really creative with some of the uses for it. They're low weight, okay, low weight. So that's important. It would lower the cost of transporting the devices. It would enable you to mount them in places you might not otherwise mount them. And potentially, not yet, but potentially there could be reduced costs through mass fabrication. It is very work intensive to create single crystal silicon, to create nice silicon that you would need for organics. And so anything that you could do to reduce the cost would make solar cells more affordable for the population. And they're also they're growing in efficiency. So they're not as efficient as your typical solar cells. However, they often said that if they could get the efficiency above 10%, it would be worth it financially to have them and not just as a novelty device. So there has been a new record, 12% as of January 2013. I think it's gone even higher since then. They're always working on it. They're always raising the efficiency. So, you know, check back for updates on that. Okay, so when you have an electron-hole pair created in an organic material, then it creates an excited state, and they call that an exciton pair. But unlike in inorganic semiconductors, the pair has a higher bonding energy. It's about 100 times greater. And in addition, the neighboring organic molecules often aren't covalently bonded to each other, as are all neighboring silicon atoms. So for example, if you have an electron-hole pair created in an organic molecule here, then the next organic molecule sitting right here is probably not bound to that one in any way except maybe weak van der Waals forces, and so it might not hop from one molecule to the next molecule. So only about 10% of the excitons result in free charge carriers. They recombine quickly. In addition, the excitons only have picosecond lifetimes. Now remember, it was millisecond lifetimes for silicon, so this is a lot shorter. And finally, they have diffusion lengths of only 10 to 20 nanometers, which compared to, you know, hundreds of micrometers, that's orders of magnitude smaller. So they've tried through various engineering tricks to get around this. So the first solar cells and photovoltaic materials that were created from organic materials, they just tried a single layer. So they had an electrode number 1, ITO, is indium tin oxide, and it's transparent, and so it gets put here on top, and then they had a layer of your organic electronic material, and then electrode 2, which was usually a metal, okay, on the bottom. You have to have the top transparent, of course, because it's a photovoltaic. You want the sun to make it through. But these had very, very low efficiencies and were basically not worth it at all. Efficiencies of only like 0.1% of the incoming solar energy getting converted to a useful power output, which is not good at all. So then they tried a bilayer where they had basically one that was N-doped and P-doped, so they had a P-N junction basically set up, kind of like in the silicon doping, similar to those solar cells. And that increased it a little bit. The efficiency was now 1%, but we're still in the not really worth it range. Okay, so what they're doing now is they're creating what are called bulk heterojunctions, or BHJs. And what they do there is they take the material that's an electron donor and the material that's an electron acceptor, basically the p-type and the n-type organic materials, and they mix them together, and then they deposit them into a single film. Okay, now generally what happens is these materials are not soluble in one another, so they don't completely mix. It's kind of like oil and water, and they form this sort of dispersed heterojunction here in between these electrodes. Okay. Now, these have much better efficiencies, 10% or so, and climbing. So that was a big leap forward. Now, remember, in order to absorb light, the films, the heterojunction there, they have to be at least 100 nanometers thick. But remember, we said that the diffusion lengths were really short. So that's at least 10 times longer than the diffusion of the excitons. And that's why the bulk heterojunctions work better than the other designs, because it's not like you had one created here and it had to move through to get to the donor side. It didn't have to do that. The p-n junction is basically all over the place, and that makes it easier for the excitons to move to the p-n junction. And so that's good. So bulk heterojunctions, as I said, have an absorption layer that consists of a nanoscale blend of donor and acceptor materials. So this drawing isn't really to scale. It's not like this is, you know, huge right here, this little region. It could be very, very small. And that large donor-acceptor interfacial area results in a higher likelihood for those short-lived excitons to reach a p-n junction interface and then dissociate. And so the bulk heterojunctions have an advantage over the layered photoactive structures, one layer and then another layer, because they can be made thick enough for effective photon absorption without difficult processing involved in orienting a layered structure. Bulk heterojunctions are most commonly created by making a solution containing both components and then casting and then allowing the two phases to separate. And the two components will then self-assemble into an interpenetrating network connecting the two electrodes. Now, as far as the electrodes go, ITO is good because it's optically transparent and it has a high work function, sorry about that, and so it doesn't absorb the incoming light. Okay, so it's transparent, that's good. And then for the back electrode, it doesn't have to be transparent, and so you just have something where you've chosen your work function accordingly, and I'll discuss that in just a second. Now you might be saying to yourself, well, I thought these things were insulators. What's going on? How does this all work? Okay, so here we go. Where's the band gap? Well, the ionization potential of a neutral organic material is the energy that's required to remove an electron from its highest occupied molecular orbital, which is sometimes abbreviated HOMO, and then that to vacuum. And then the electron affinity is a measure of the material's ability to act as an electron acceptor, and it's often approximated as the lowest unoccupied molecular orbital, or LUMO. And that level is relative to the vacuum of the organic material. And then the HOMO-LUMO gap, or band gap, of the conjugated organic material is the minimum energy required to promote an electron from its HOMO level to its LUMO level there. And this band gap in organic semiconductors is typically around 1 to 4 eV. So the difference in ionization potentials in your device actually establishes an internal electric field that causes the diffusion of the electrons in the holes. ITO is good because it has a high work function, so that's sitting up here. And then you kind of want it to stair step, right? So you have your high work function, and then moving into your donor, moving to your acceptor, and then moving to your cathode, which is your aluminum or something like that, okay? The metal electrode needs to have a low work function, okay? So here's your low work function for your metal, here's your high work function for your anode, and then there's kind of the stair step there. The work functions of the bilayers should be as in the diagram, and that helps allow the transport of the electrons in the holes to the electrodes easily. And the energies of the conducting polymer must lie at higher values than the fullerene material, which is the acceptor material. So that PCBM that I showed you earlier, that's the fullerene type material, that's your acceptor. So these, this is a plot of a table from Sigma Aldrich, and it shows you whether it's a p-type or n-type material, and also what the energies of the LUMO and the HOMO are. Okay, so these are polymers that are soluble in the same organic solvents. So what you do is you take your polymer, whatever you've ordered, you dissolve it in something like chloroform, for example, and you dissolve them both in the chloroform, and then you've got it blended and mixed. Then you put it onto your surface somehow. There's various techniques. Spin coating is a really popular one where you just kind of drip the material onto the surface while you spin it, and that makes a nice flat film. And then as it dries, it solidifies into a good thin film with thicknesses that are dependent upon how fast you've spun it. So the band gaps that you see here are around 2 electron volts for these materials, right? So if you look at it, it goes like minus 3.7 to about 6.1, so that's a difference of about 2-ish eV. All of them have about that much of a difference. Now, with a band gap of 1.1 eV, which is similar to silicon, we can harvest about 80% of all incoming solar radiation, and that's because of the energy of the solar radiation that's coming in. Remember, E is equal to HF, or HC over lambda, for a photon. And so if you have a lower band gap, then you can capture more of the radiation coming from the sun. But with a 2 eV band gap, it's a little bigger. This drops to about 30% of that incoming solar energy that's harvested. Okay. So I can't emphasize enough how important structure is in terms of the bulk heterojunction. It's super important. The network of the donor acceptor must be well mixed, and it must be interpenetrating. You have to have a good interface established between your acceptor and your metal also, and your donor and your ITO. Otherwise, you're going to get recombination and it's not going to work. Only about 10% of the photoexcitations lead to the free charge carrier, so you want to make sure that you get your bang for your buck. Okay. In fact, right now I'm working on a research project where we're exploring the structure of the bulk heterojunction, and then they're correlating that to device performance. And as you tweak the structure, you can get better device performance, and they're trying to figure out how to optimize that in order to up the efficiency of the solar cell. So there's a few parameters that you have to think about when you're looking at device performance. One of those is electron mobility. Now, what is this? Well, in solid-state physics, the electron mobility characterizes how quickly an electron can move through a metal or a semiconductor when an applied electric field is there. In semiconductors, there's an analogous quantity for holes called hole mobility. So you have two mobilities, basically, for an intrinsic semiconductor like silicon. You've got your electron mobility and your hole mobility. And the term carrier mobility will in general refer to the combination of those two, combining the electron and the hole mobility. Now, when an electric field is applied across a piece of material, the electrons are going to respond by moving with some average velocity called the drift velocity that we've discussed in a previous lecture. And then the mobility is defined as the via its relationship to this drift velocity. So you have your drift velocity is equal to your mobility, often symbolized with a mu, times your electric field strength. So electron mobility is almost always specified in terms of some non-SI type units. It's not meters squared, for example, it's centimeters squared per volt second, okay? So that's different from the SI unit of mobility. So conductivity is actually proportional to the product of the mobility and the carrier concentration times the electron charge. So sigma is going to equal to the density of electrons, number of electrons per unit volume, times the electronic charge E times the electron mobility. Okay? So for example, the same conductivity could come from a small number of electrons with a high mobility or a large number of electrons with a small mobility, right? Does that make sense? So for metals, it wouldn't typically matter which of these is the case, since most metal electrical behavior depends upon conductivity. And so mobility is pretty unimportant in metal physics. On the other hand, for semiconductors, the behavior of the transistors and the other devices can be very different depending on whether there's many electrons with low mobility or few electrons with high mobility. So mobility is almost always a very important parameter for semiconductor materials, and almost always a higher mobility leads to better device performance when all other things are equal. So in a semiconductor, it's also a pretty valid formula to link it to the number of holes. When you have your conductivity and it's due to the holes, then you have PE mu sub P, where P is the density of holes or the number of holes per unit volume. E is yet again the charge, 1.602 times 10 to the minus 19 coulombs, and mu sub P is the mobility of the holes. And if you've got both electron and holes, like you would in an intrinsic semiconductor like silicon, then you just sum up the two expressions for the electrons and the holes to get the total conductivity. Now, what are some example values of mobility? Typical electron mobility for silicon at room temperature, roughly 300 Kelvin, is 1400 centimeters squared per volt second, and the hole mobility is around 450 centimeters squared per volt second. We have seen some very, very high mobilities in some of these carbon structures. For example, in carbon nanotubes, they've seen mobilities of 100,000 centimeters squared per volt second. So that's kind of your ballistic transport, if you will. And more recently, graphene, which we haven't discussed yet, it has mobilities of 200,000 centimeters squared per volt second. Now, organic semiconductors, after all that, sound pretty pitiful. They have carrier mobilities below 10 centimeters squared per volt second, okay? Now, what limits mobility? Well, by definition, mobility is dependent upon the drift velocity. So the main factor determining drift velocity is the scattering time, how long the carrier is ballistically accelerated by the electric field until it scatters with something that changes its direction or energy. The most important sources of scattering in typical semiconductor materials are ionized impurity scattering and acoustic phonon scattering, also called lattice scattering. In some cases, other sources of scattering may be important. We're not really going to talk too much of those, but neutral impurity scattering, optical phonon scattering, surface scattering, defect scattering, these are also important. So let me define ionized impurity scattering. Semiconductors are doped, remember, with donors or acceptors, and those are typically ionized and they're charged. And then there's Coulomb forces that will deflect an electron or hole when it approaches that ionized impurity, and that's ionized impurity scattering. So basically it's scattering off the dopants. And phonon scattering, I don't know if you've heard of this, but phonons are basically sound waves. And at any temperature above absolute zero, these are vibrating atoms, and they create pressure waves, acoustic waves in the crystal, and those are called phonons. So it's basically a movement of sound or pressure motion through your material. That's a phonon, maybe a new term for you. Like electrons, phonons can be considered as particles, okay? And a phonon can then interact or collide with an electron or a hole and scatter it. And at higher temperatures, there's more phonons and therefore increased phonon scattering, which tends to reduce your mobility. In organic solar cells, however, as opposed to the silicon, the mobility of the charge carriers isn't necessarily a material property the way that it is for a semiconducting material. So that 10 centimeters squared per volt second thing that I dictated to you, maybe it's not as important. It's a device property, okay? And that's because the mobility is sensitive to the nanoscale morphology of the thin film. In other words, the structure of that bulk heterojunction dominates. It's really super important in saying what your mobility of your device is going to be, and thus dictating the device performance. It depends on the preparation techniques. There's parameters like what kind of solvent you use. Did you use chloroform? Did you use toluene? What did you use? What was your evaporation time? What was the temperature of the substrate when you did all that? Did you do any annealing or heating of it after you deposited it? And what was your deposition method? Okay. So for example, here's some studies that I'm going to quote and show you cool pictures from where they studied device performance and its how it went along with the preparation of the device. So Shaheen here and colleagues showed that changing the solvent from toluene to chlorobenzene when you were spin casting your films increased the efficiency of the solar cells by nearly a factor of 3. And they cited the reason for this as changes in the structure of the solar cells on the nanoscale. So here's some AFM images of some films that they used. The one on the left was where the polymers were dissolved in toluene, and the one on the right is where, I'm sorry, not polymers, but organic molecules were dissolved in chlorobenzene. And you can see that the structure is different. The length scales depicted here are the same, but you get kind of a smoother, bigger substructure here on your toluene films than you do in your chlorobenzene films. And of course, that can be linked to maybe how the bulk heterojunction is. If you've got a lot more domains there where you have your N-type and your P-type meeting up in smaller regions and domains, then that's better, right, for your device. And so that's shown here. You can also change the weight ratio between your P-type and your N-type organic material. And that can also greatly change the structure and device performance. So studies have shown that the PCBM, which is your N-type, is going to form clusters in the matrix of the P-type material, which is here MDMO PPV, which you can look up. But basically, it just shows how the structure has changed with different weight ratios. So here you have a 1-to-1, here you have a 1-to-2, here you have a 1-to-3, here you have a 1-to-4 weight ratio, and then the film is shown here in a slice cross-sectional view as well. What that looks like. So the cross sections show that the clusters actually have a skin around them that's a more homogeneous blend of the two materials. So that affects the device performance. And then finally, some studies have shown that switching up whether you use C60 or C70 gives higher efficiency solar cells. So studies have shown that the structure of this blend is lamellar, better suited to solar cells than the PPV-based materials. So there you go. So the structure of the bulk heterojunction affects everything. Buckyballs can be used as organic solar cells and making the films in those, and I hope you learned a lot. So if you have any questions or if you need anything, please get back to me, and I'll see you in the next lecture.